Okay, now let's move on to the second speaker of the session, and so it's going to be Jitendra Prakash, and he's going to talk about constant size robust self-tests for states and measurements of unbounded dimensions. Okay, so I give you the floor.
Thank you, Frederick. And I would definitely like to thank the organizers for organizing such a wonderful conference. I think online is definitely the hardest part, but it was great. And also I'll thank the organizers for giving me a chance to speak about my research. So today I want to talk about my research with Laura Mančinska and Chris Schafhauser on constant size robust self-tests for states and measurements of unbounded dimensions. So let me briefly tell you what self-testing is about. So it's a group of techniques in quantum information to infer, say, the quantum mechanical description of a quantum device just from classical observations. So we want to look at the statistics obtained from the quantum device and then want to infer, for example, what the state of the quantum device could be. This has plenty of applications going from device-independent quantum cryptography to entanglement detection, investigating the structure of quantum correlation set, and in quantum complexity theory. In particular, we have seen that it has been used extensively in this recent breakthrough of MIP star is equals to RE. You might have from Thomas Widig's talk. So, and one of the important implication is the negative resolution of the cone embedding problem, which was open since the 70s. So let me also give a general scenario of how self-testing is applied. Suppose we have two. So here I will try to keep things simple, and we can just think of a quantum device as being having two players and sharing the state. So suppose Alice and Bob, they are spatially separated and they share a quantum state, and each has a quantum device. This device has n measurement settings, and its setting has k outcomes, which I will label as 1 to n for the measurement settings and 1 to k for the outcomes. And Alice and Bob, they can choose any of these settings and then look at what the outcome of the device is. So they eventually will get a probability distribution given by this number Pij given Vw, which is the joint conditional probability that Alice gets outcome I and Bob gets J, provided that they perform measurements settings V and W. So what self-testing allows us to do is that we want to look at this correlation Pij Vw, and then we want to understand what the quantum state or the quantum measurements that Alice and Bob have been using. So this is like the most general setting in which self-testing is applied. Now, let me talk about these settings, how these measurement settings are given mathematically. So we usually talk about these quantum strategies, which is given by a state in some finite dimensional Hilbert space, the tensor product of two Hilbert spaces, and AVI and FWZ. These are these positive operators, such that if I look at each measurement setting, then I should be able to get identity if I sum over all I. And similarly for Bob, if I look at FWJ and sum over J, I should get identity for Bob. So this basically say that we can have at least one outcome from each measurement settings. So from these strategies, one can get the joint conditional probability that I was talking earlier. This is given by the tensor product of these two operators applied on the state and then taking the product with the state. So one example of one well-known example of self-testing is the CH is in form of a CHSH game. So it's a well-known non-local game where we have 2 input and 2 output. So think of these as 2 measurement settings and 2 outcomes for each Alice and Bob for each of these settings. And it's well known that if we use quantum resources, then one can get better winning probability if than using classical resources. So in fact, we know that the maximum quantum winning probability is given by 0.85 compared to the classical one, which is 0.75. And in that case, in the maximum case, one uses the strategies given by the maximally entangled state on C2 tensor C2, and these tilde operators given by Z and X for Alice, and these operators given for Bob. Here, Z and X, they are the poly Z and X. So one can ask then that, well, if we have any other strategy which also achieves the same quantum value, then what can we say about that strategy? Then one can show that, well, actually one can find isometries going from the space in hand. So for example, here I've taken the state to be in CD tensor CD. For Alice, going to C2 tensor some junk space, and for Bob also going from the space in hand to C2 tensor some junk space for Bob. And there's some junk state such that if I look at the state AI tensor BJ applied on psi, then the isometry takes to the one with the canonical measurement operators applied on the maximally entangled state, tensored with that junk state. So in other words, there's kind of a unique quantum strategy which can be related to every other perfect quantum strategies. So this is one canonical example of self-testing. There's also a reversed version in which one can ask, what about those strategies which yield quantum winning probabilities close to 0.85. So in that case, we have a robust version. This says that if we look at if the winning probability given by that strategy is epsilon close to the maximum one, then one can see that one can show that well, this equality can be replaced by some approximation up to some delta, which is like function of epsilon, and that relates to the canonical state applied on the canonical measurement applied on the state, and so the junk state. So in our case, what we want to well, yeah. So before that, let me talk about how the proof goes in. Well, one of the proof goes. So this is due to Thomas Wittig. So in this case, what we do is we associate a group to the CHSS game, and here this group is the dihedral group of order 8. And then one shows that if we look at perfect strategies, then that leads to a representation of the group. And if you look at approximately perfect strategies, then that leads to some notion of approximate representation of, again, the dihedral group of order 8. And then to get the isometries that we want in our earlier slide, one uses the Gowers-Hatami theorem to relate this approximate representation to the canonical one. And then we tie up all these things together to get our final statement in the CHSH case. So in our work, we do not work with a game, but we work with the strategies and the correlations obtained from the strategies. So what we do is we start with, say, n projections of size d cross d. And these projections have this nice property that if we sum it up, then we get some scalar times identity. And for sake of, say clarity, we can let's take this scalar to be some fraction b over d, such that they are in the lowest terms. Then we want to look at those scalars and those projections which have also the property that they are unique in some sense. That means if we have any other projections, P1 till Pn, then and they sum up to X times identity, then that Pi factors as identity tensor the smallest one that we have, that in the smallest dimension possible. So in other words, if you look at say the algebra generated by these projections, then the projections living in the smallest dimension are the only representations of that algebra. So in other words, they have a unique irreducible representation. And so yeah, we look at this set of scalars, which we denoted by lambda n. So to keep it simple, let's think of an example where we can take, say, n unit vectors in Rn minus 1, which form the vertices of a regular n simplex into the origin. So for example, if you just look at n is equals to 3, then that forms a Mercedes-Benz frame in R2. And then we look at the projections corresponding to each of these vectors. And one can see that if we sum of the projections, then that should sum up to n over n times n minus 1 times identity. More about these projections and what scalars they have and the representation theory about these projections can be found in this paper by Krukliak, Abanovich, and Samoilenko from 2002. So we want to get a quantum strategy from these projections, and for that so these tilde ones, they are the smallest possible projections. I mean, the smallest dimension they can live in. And then from those projections, we take them as Alice's operator, and for Bob, we just take the transpose, and we use the maximally entangled state on D cross T. And let's call this script S and X tilde to be this canonical quantum strategy that we are looking at. And then we look at, say, these correlation, the quantum correlation obtained through these strategies. So for each n, we will get, for each n and x, we will get these correlations. And of course, n vary can be bigger than or equals to 3. So we established that if we have a quantum strategy which induces a quantum correlation P, which is close to the ideal one, then that strategy should also be close to the ideal quantum strategy given by the tilde ones. And in other words, here's the main result. So for every epsilon, and for every epsilon, we can find a delta such that if I have a strategy S, script S given in this form, which yields a correlation P, and P is close to the tilde correlation up to some delta, then the strategy S is approximately related to the tilde strategy via local asymmetry, which has the same form that we have in the case of CHSH. Okay, as I had outlined earlier, the proof of CHSH self-testing is kind of the motivation of the proof that we use, but with some differences. So in the case of CHSH KEM, we used a group to associate with it, but in this case we use an algebra, or in other words, we use C-star algebra, which is associated to the relation of to this relation that the projections, they sum up to a scalar times identity. And then we follow the same template that we show that approximate strategies, or like perfect strategies that lead to perfect approximations, perfect representations of the C-star algebra, and approximate strategies lead to approximate representations of the C-star algebra. And the Gowers-Hatami theorem that I mentioned earlier, here is the analog that we use. And this is the hardest part that we have because it's because of one thing that I will say in a moment. So what the Gowers-Hatami theorem tells us that if we have some approximate representations which is given by, say, E1 till En. And these are positive operators. They are approximately projections, and they approximately sum up to X times identity. Then I can relate each of these EIs to the canonical ones up to some isometry, conjugated by an isometry. And here, this rho sub A is state-dependent distance that we have to take care of in all these circumstances. So there's one distinction between the proof of Gowers-Hatami and this analog is that here we do not have a constructive proof, and therefore the epsilon and delta dependence in our main theorem is we do not know what's the exact dependence. Okay, so let's talk about some corollaries that we get from our main theorem. So if we just look at, say, 4 projections, so we are in the case of n is equals to 4, then again from that Kruglia-Kramenovich Samoilenko paper, we know that there exist 4 rank k projections like these, which sum up to these distinct scalars times identity. Therefore, just by an application of our main theorem, we get that we can robustly self-test each of these strategies coming from these 4 projections. The nice thing is that the scalars here have denominator 2k plus 1. So that means we can robustly self-test each of these maximum entangled state in this 2k plus 1 dimension. So that leads us to some known results that we know from before. So for example, we know that any pure bipartite entangled state in CD tensor CD can be self-tested from a correlation with 3 inputs and D outputs. This is from the work of Prodangelo, Goenes-Carani from 17. And we also know that for each D in some infinite subset of primes, the maximum entangled state of local dimension 4D minus 1, 4 times D minus 1, can be robustly self-tested from correlation with roughly 100 inputs per party, which is the result of Wang-Fu from 2019. So based on the corollary that we just saw, we can have we can write down, say, that for each odd dimension, the maximum entangled state phi sub D can be robustly self-tested by quantum correlations with only 4 inputs and 2 outputs. So we have like a constant size self-test for each of these maximum entangled states living in odd dimensions. And also we see that, the 4 projections that we saw in the corollary just before, they are of rank K. So, and this K is unbounded, so we can also robustly self-test these projections of unbounded rank with just 4 inputs and 2 outputs. So one of the hopes from our work is that this analog of Gowers-Hatami theorem could be improved by, say, getting exact dependence upon like what the epsilon and deltas are instead of an indirect proof. And also, like, where can we apply these things to some classes of some non-local games which are called synchronous. And since there are plenty of them, I hope that we can there could be some more development on the self-testing of these kind of non-local games. So with this, I think I would like to end my talk with these references. Thank you for listening.
Okay, thanks a lot, Jitendra, for this very nice talk. So we have lots of time for questions, actually. So I'd like to open the floor for questions. And while the questions start coming in, I'd like to ask one as well. So one way to get this condition of having a bunch of projectors that sum to a constant times the identity, or at least something approximate to it, would be to just choose them at random according to the Haar measure. Does that give anything interesting?
I'm not sure that Yeah, I don't know actually to comment.
Okay, fair enough.
Well, I mean, these the scalars that we get, they're pretty well defined. So I'm not sure like how random we could.
Right.
Get.
Actually, so when you say approximate, maybe I missed this, but what norm do you use, or what like?
Oh yeah,
what's your measure?
in the approximate case, we use the norm obtained from the state of the strategy. So for example, if we look at say this state, the state here, then we look at the reduced density matrices of Alice and Bob respectively. So then we compare these projections. Well, in this case, it's on Alice's space and this one on Bob's space.
Okay, so you just look at let's say the winning probability or something like this as your.
Yes, well, not exactly. For in the CHSH case, we look at the winning probability, but here we look at the whole correlation table.
Okay, and then you have a norm on this?
Yes, for comparing the norm of the correlation, we can use, I mean, we can use either the one norm or the two norm, but since all of them are equivalent, so it doesn't really matter.
I mean, so equivalent meaning, because I mean, it's infinite dimension anyway, right? But
yes, yeah. But
I mean,
in
so
our
if
work,
you
yeah,
have
we use the one
quantitative
norm.
bounds, yeah.
Yeah.
Okay, so this is the one norm that you have.
Yeah, this is the one norm.
Okay, I see. Huh. So yeah, I guess if you have hard random states, somehow I guess it's what the canonical choice would be. I'm not sure what that would be. Like what you would relate it to.
Yeah.
Yeah.
Yeah, I'm not sure like how even approximately how it will be generated.
So yeah. Yeah. So nobody's been asking questions in the Slack, so I guess we're just gonna wait for a few minutes before the next talk starts, since we advertised that we will start at 12 past.